Hello friends, so today we are going to continue with the chapter electrostatic, and today we are going to solve 4 questions from electrostatics. And the first question, it is given so first question states that a ring with the radius r has a uniform positive charge density lambda. A particle with a positive charge q and mass m is located at the center of the ring and is then given a tiny kick. If it is constrained to move in the plane of the ring, show that it undergoes simple harmonic motion for small oscillations and find the frequency. In this case, we are going to find out the frequency of the oscillation, and we are given the ring and the charged particle which is placed at the center, and we are also given that the radius of this ring is given as capital R, and this charged particle is having a positive charge of q and its mass is given as m, and the ring is having a uniform charge density of lambda. So therefore we can find out the total charge on the ring. We can say that total charge on the ring, and let us suppose that is our capital Q, then this capital Q will be equal to 2 pi r times lambda. Okay. And so let us consider a, you can say, small charge distribution on this ring. Okay. And this small charge distribution is, let us suppose, our dq. So this is small charge distribution dq, and this small charge distribution is making an angle of d theta at the center. Okay. So we consider a small charge element and that charge element is our dq. Then we can say this dq will be equal to lambda time r multiplied by d theta, and we can find out the distance between the particle and this element. Particle is at the center, so we can say that our distance between the particle and the element, and that element is our dq. Let us suppose that distance is given as s, and for the to find out s we are going to use the cosine law. Okay. Therefore, we can write this as our s square will be equal to this is our r square plus for the small displacement is our small r square, and this comes as minus 2r small r cos of theta. Okay. And here this small r is the displacement of the you can say this particle from the center. So this small r is displacement of the particle from the center. Therefore, we can rewrite this distance equation as S will be equal to r square plus small r square minus 2r small r cos of theta and its square root. And now we find out the potential due to this small element. Potential energy due to element, okay, small element which we have considered, and this small element is having a charge dq. Therefore, we can say that its potential energy du will be equal to 1 upon 4 pi epsilon naught. This comes as q dq and the distance between this. Now we substitute value of dq and value of s, and we can write this as 1 upon 4 pi epsilon naught, and this is our q, and dq was our lambda r d theta, and s was our r square plus small r square minus 2r r cos of theta and its square root. And from the denominator, this part we are going to take r as a common. We are going to factor out it. Therefore, we can say that our du will be equal to 1 upon 4 pi epsilon naught, and we get this as q lambda r d of theta. R we factor out, so this comes as 1 plus r square minus 2r r and cos of theta and its square root. And this, in order to solve this denominator, we are going to use the Taylor expansion, and for that we are going to assume that this is equivalent to some variable. Okay. So we are going to assume that epsilon is equal to r square upon capital R square minus 2r r cos of theta. Therefore, only the denominator part we can write this as 1 upon 1 plus epsilon and its square root. And its Taylor expansion can be approximately written as 1 minus epsilon by 2 plus 3 epsilon square by 2 and so on. Okay. And we substitute value of this epsilon, and we get this will be equal to our 1 upon s, because this is nothing but our s, so you can say 1 upon s will be approximately equal to, and this is our 1 upon r, so 1 minus 1 upon 2 we have r square, capital R square, minus 2 r cos of theta plus 3 by 2, and then it is square, so this comes as 4 r square, capital R square, cos square of theta. And we can further solve it little bit, and this will be equal to our 1 upon r, and we can combine the terms, and we can combine these two terms, they are all same, so we get this as our 1 plus, this comes as r upon r cos of theta plus r square upon capital R square, and this comes as our minus 1 by 2 plus 3 by 2 and cos square theta. Okay. And now we can find out this total potential energy for complete ring. So you can say total potential energy, that is our u, for the sake let us write this is u of r, will be the integration of our du. Now we can simply substitute the limits, okay, and we can take the constant part outside the limit, so that will be q lambda, and we have 4 pi epsilon naught, and integration, this will be coming as 0 to 2 pi, and we are left with 1 plus r small r cos of theta plus r square upon capital R square minus 1 by 2 plus 3 by 2 cos square theta. So obviously the integration will be associated individually by this part, through this, as well as through this part. Okay. And the integration of this cos of theta will be equal to 0, so this will be just gone away. Okay. And cos square theta will be giving us our pi. Therefore, we can write that our energy, total potential energy, electrostatic potential energy U of r will be coming equal to as q lambda 4 pi epsilon naught, and we get this as 2 pi plus pi r square upon 2 capital R square. And so this can be further written as, and you can say that our u of r will be equal to, this gives us q lambda upon 8 epsilon naught r square, and this is r square. Okay, because if you multiply this inside, we are going to two parts. First part will be entirely constant, okay, that is not dependent upon this r, so we can simply ignore it. Okay, that is only simple a constant addition. So we are only interested in the variable, you can say the part which is dependent upon this r. Okay, because r is the distance through which the particle at the center is being moved. Okay, so we are only interested in this r. This constant part is simply a, you can see, amplification part, nothing more than that. Now from here we can find out the force equation. So you can say force and equation of motion. We know that the radial force that is our Fr, will be giving us the negative of the derivative of our electrostatic potential energy with respect to R, and therefore its derivative will be giving us q lambda, and this comes as 4 epsilon naught R square, and this is R. Okay, we simply ignore the constant term. Even if we keep this constant term in the equation, this derivative of this constant term will be equal to 0, so there is no purpose of writing it. And in terms of this you can see acceleration, we can write that this radial force is nothing but our m r double derivative is equal to minus q lambda upon 4 pi epsilon naught capital R square and small r. And we can make a comparison this with the standard equation, which is our acceleration, that a double derivative of a radius, not radius but you can say the portion with which it is being moved, plus r is equal to 0. Therefore, from here we get that our omega square will be equal to q lambda, I think, yeah, this is correct. So this comes as 4 pi epsilon naught m r square. So this is the frequency of the oscillation. Okay. Now we come to the second question, and second question states that a charge dq is 2q is at the origin and charge minus q is at x equal to a on the x-axis. Find the point on x-axis where the electric field is 0. Consider a vertical line passing through the charge minus q, that is the line given at x equal to a. Locate at least approximately a point on this line where the electric field is parallel to the x-axis. So let us draw the, you can see, basic figure. So everything is lying on x-axis, and we are given that we have charge 2q which is at the origin. So this is our origin, so this is our 2q, and we have a charge of minus q that is at x equal to a. Okay, so this is the line at x equal to a. So this distance will be our a, and the coordinate of this will be equal to a comma 0. Okay. So this is the basic figure. Okay. And we have to find out the point on x-axis where the electric field is 0. That is our part A. Part A, electric field on our x-axis should be equal to 0. We have to locate that point, and this is our origin. Okay. And let us divide, or we can say make a directional analysis with respect to the electric field. Okay. So we can divide this entire zone into 3 parts. Okay. So we can say that we have our direction analysis, and we are going to divide it into regions. First region we are going to consider, this is a first region, this is second region, and this is our third region. We are going to consider 3 regions. So we have our region 1, and region 1 is when x is less than 0. And let's find out what will be the direction of the electric field because of the charge 2q and because of the charge minus q in this region. Only direction, from that we can just draw a conclusion whether the electric field possibility will be 0 or not. Okay, and that possibility is quite obvious if the direction of electric field in any region is opposite. It means, suppose because of this 2q is towards the left and because of minus q is towards the right. Okay, so both the electric fields are in the opposite direction, so therefore the possibility of cancellation those electric field is quite high. So under those circumstances the electric field can come equal to 0. But if at any point the direction of electric field is same, whether toward right or toward left for both the charges, then the cancellation is not possible, so electric field cannot be equal to 0. Okay, so this is basic, because we are only interested in finding out the electric field should be equal to 0. So in region 1 we can say that our field due to our plus 2q charge is to left, okay, or we can say this is our in terms of the unit vector, and then we have our minus q charge. So you can say the field due to this minus q is toward x equal to a. Okay, x equal to a is nothing but toward right, x toward a, or we can say it is toward right plus x unit vector. Thus we can draw a conclusion that fields are opposite. Fields oppose, therefore we can say possible cancellation. Possible cancellation. Okay. And then we come to our region 2. And region 2 is our x is less than a but greater than 0. Okay, this is region 2, and for in region 2 the electric field direction is both toward the right, so that is no possible of cancellation. So you can say that both fields point to right, which is plus x unit vector, therefore we can say no cancellation. And finally we come to our region 3, and region 3 is our x is greater than a. And for x is greater than a, we have our field due to plus 2q is towards the right, that is plus x unit vector, and field due to minus q will be to left, that is our minus x unit vector. Therefore we can say fields are in opposite direction. Fields oppose, and if they oppose, we can say there is a possibility of cancellation. Possible cancellation. So a region of interest are only our two regions of interest. First is our region of interest is third region, and is our first region. This is not our region of interest because there is no possibility of cancellation. So let us start one by one, because we are only interested in the magnitude part. Okay. So we can say that our region of interest are our region 1 and region 3. Okay. So we are only interested in the magnitude condition. Okay. So we can say that our magnitude condition, and for any general point x, okay, magnitude condition for, or we can say at any point x, we can write this is 2 upon our x square should be equal to 1 upon x minus a whole square. Okay, because charge and 1 upon 4 pi epsilon naught, everything will be cancelling out, because they belong to both left side as well as right side. And we can write this equation as our x square minus 4ax plus 2a square is equal to 0. Or from here we can write that our x is equal to a 2 plus minus square root of 2. Okay. So let us evaluate both positive as well as negative values. So we can say that our x is equal to our a, and this comes as 2 minus square root of 2, and square root of 2 is approximately 1.414. Therefore this will be approximately equal to 0.586 times a, and this is lying between 0 less than x and less than a. Okay, so this is invalid. And next is our a 2 plus minus square root of 2, and that will be approximately equal to 3.414 times a, which is obviously greater than a. Okay. So it means it lies x greater than a, and this is our valid. So our x is equal to a 2 plus square root of 2. At this position we are going to get that our electric field on x-axis will be equal to 0. Okay. And now we come to part B. And part B states that we have to find out that the electric field, which is parallel to x-axis, okay, we have to find out the point. Okay, sorry. So we have to find out the point. You can see point on x equal to a. Okay, and at this particular point we are going to get that our electric field should be parallel to our x-axis. Or in simpler terms we can say at this particular point the electric field in vertical direction should be equal to 0, because then only the electric field will be, only the parallel component will be left, the vertical component should be equal to 0, it should vanish out. And for that let us redraw the figure. So this is our x-axis, one charge we are having is our 2q, and this is our minus q, and this is our x equal to a. And we assume this can be in the positive side as well negative side, that doesn't matter. So we assume that we consider a point P, and the coordinate of P will be equal to a comma y. So we consider this is our y, and this is our a. Therefore our distance r will be equal to a square plus y square root. And we have to find out at this point P, or it can be in the negative side also, that doesn't matter, only the, you can say, the vertical component should be equal to 0, then only we are going to get that parallel electric field should be parallel to its x-axis. Okay, that's the only at this point P. Okay, so this point is our P point. Okay. So let's find out what will the field due to this minus q at and let's find out field due to minus q. Okay. And we are interested only the vertical part, okay, because we are going to take vertical component is equal to 0, so horizontal component will be non-zero. And so you can say that purely vertical let's write this as an electric field due to charge minus q in vertical direction, and it is going to have both values depending upon the point P, if point P is on the positive side or point P is on the negative side. Okay. So we can just write its both equations. So this will be E minus q y, and it is going to have two things, that is minus k q upon y square, and this is whenever y is greater than 0, and this will be plus k q upon y square if y is ever on the negative side. Now we find out the field due to this plus 2q. And field due to plus 2q, and for that distance we already know, therefore once again we are only interested in the vertical component. Okay. So you can say that the field due to 2q in vertical direction will be equal to our k, and this is our 2q upon r square, and this will be y upon r. Okay, this is quite standard relationship, and if you want we can still make an approximate. So we have this is our 2q, and this is our point P, okay, and this is, let us suppose, angle theta. So this is our r. So electric field is going to have two components, okay, and we only interested in the vertical component. So this will be our vertical component E2q y, and okay, one second, let me. So this angle will be what, 90 minus theta, so this will be also 90 minus theta, so this will be theta. So there will be a cos of theta, and that will be giving us y upon r, because this is r and this is y. So we are only interested in, please remember, we are only interested in the vertical component, because we are going to put vertical component is equal to 0. Then only the parallel component will be left. Okay. So we have kept this in mind. And so now we come to our final part, that is condition for horizontal net electric field. Condition for horizontal net field, and there is only one condition for that, that our electric field in vertical should be equal to 0. Okay. And we consider the formula for y less than 0, and due to symmetry y greater than 0 will be same. Okay. The solution will follow this y less than 0, only the sign will be different. Therefore we can say that the electric field due to charge 2q plus electric field due to charge minus q in vertical direction should be equal to 0. So we simply substitute them. We get this as our 2y upon a square plus y square, and this comes as our 3 by 2 plus 1 upon y square is equal to 0. Here I have just removed all the constant things, because this k and this q will be all gone away, and this will be our r, we know is our a square plus y square square root, and this will be r cube, and we substitute it, we get this answer. Okay. And now it is quite little bit tricky to solve, okay, but we can, because in the question it is asked to find out the answer approximately, not the exact one. So let us assume that our y is equal to minus of z, and where z is greater than 0. Okay, please keep in mind we are discussing it y for less than 0. Therefore we get this as our 2 of z upon a square plus z square 3 by 2 is equal to 1 upon z square. And here this putting using this negative sign is solving us only one purpose. If we don't put a negative sign, okay, if we assume that this is a positive, so we are going to get here a negative sign. In order to just avoid that, we just use it as a negative sign. Nothing else is much of the difference. Okay. And therefore we can write this as our 2z cube is equal to a square plus z square 3 by 2, or we can say that our 4z6 will be equal to a square plus z square whole raised to power cube. And we can use here a solution, sometimes it is also called as a non-dimensional form, okay, and that is one of the method to solve some of the critical equations. So we are going to use non-dimensional form, and for that we are going to assume that z is equal to a constant c times a, okay, because z is nothing but the distance and it will be a multiple of our a, so c times a, and therefore this helps us in solving for our a. So this comes as 4c6 is equal to 1 plus c square and whole raised to power 3, and this approximately gives us that the value of c will be equal to 0.86. Therefore, we can write that our electric field will be parallel to x-axis at the coordinate x comma y, and that will be equal to our a plus minus 0.86 times a. So we found out that at this particular coordinate we are going to get electric field will be having an entirely parallel component. Its vertical component is going to vanish. Okay. So this was our one of the question. Okay. And we come to our next question. It states that a half infinite line has a linear charge density lambda. Find the electric field at a point that is even with the end, a distance L from it, as shown in the figure. You should find that field always point up at 45-degree angle independent of L. So we can just draw a approximate figure for that. And we are given that this is half infinite, so it is going to start from one end at the origin and other end will be going to infinity. And we have to find out electric field at a point that is even with the end. Okay. So this is our end. So electric field at a distance which is even with the end. So this is the line which is even with the end, and let us suppose we denote a point P, and this point P is at a distance L from this end. So we have to find out the electric field at point P. Okay. The phrasing of the question is a little bit, you can say, typical rather. Okay. But if you draw the figure, we can clearly find out. Now we have to find out the electric field at point P in case of a semi-infinite line. Okay, that is, I think, one of the easiest part to do in electrostatics. Okay, but here the question was framed: find the electric field at a point that is even with the end. Okay, so this, because this is semi-infinite, the other end will be to the infinity. So the only possibility is of our end is at the origin, and the point P should be in line with this origin. Then it's called as an even point. Okay, and this point P is at a distance of L. Okay, so this is the different way of rephrasing the, you can say, regular question. Rest of the question is quite easy to solve. And once again, so we are going to consider a small charge distribution, that is of dq, and that is at a distance x. And we are going to find this, and this will be our R. Okay. Therefore, we can find out that our this R will be equal to our x square plus L square and its square root. And we are going to write in the both vector form as well as magnitude form. So let us say that consider a small element dq at a distance x from origin. Okay. And you can write that the vector form dq the vector from this element dq to p, and that vector is our r vector, and that will be equal to our minus of x unit vector plus L y unit vector, and its magnitude will be equal to over x square plus L square and its square root. And let's find out the electric field at point P due to this dq. Field at P due to dq, and we are only interested in the magnitude part, so we can say this small electric field dE will be equal to 1 upon 4 pi epsilon naught, and this comes as our dq upon r square. And in terms of charge density, we can write this as 1 upon 4 pi epsilon naught, and lambda, and this is dq and its length is suppose dx. So this becomes lambda times dx, and we got this as x square plus L square. And we can write the unit vector. So you can say that our r unit vector will be equal to minus x unit vector plus L y unit vector divided by x square plus L square and its square root. Therefore, we can write that our electric field vector form will be equal to our k lambda, and we get this as our minus x unit vector plus Ly unit vector, and we have this as x square plus L square and 3 by 2 times dx. Now we can find out the component of the electric field. So we can say its x component will be equal to minus k lambda, and it comes as our x upon x square plus L square 3 by 2 dx, and its y component will be equal to our k lambda L dx x square plus L square and 3 by 2. And now we can simply integrate them for our complete part. So you write that our x component will be equal to minus k lambda, and for x integration goes from 0 to infinity because it is semi-infinite, and we have this as x dx x square plus L square and 3 by 2. And this is quite easy. We can just assume that this x square plus L square is equal to u and substitute it. So I'm just going to write the answer directly. So we are going to get the electric field in x direction, E of x will be equal to minus k lambda upon L. Similarly, we can integrate for our y direction. So this will be coming as our k lambda L integration dx x square plus L square 3 by 2, and our y component will be giving us 0 to infinity, and this y electric field will be equal to over k lambda upon L. Now we come to its direction as well as the magnitude. So we can say that our magnitude is our same except with the negative sign. And So for direction, that is our tangent of theta will be equal to our E of y and E of x and its magnitude. Obviously, that is equal to 1. So we get our theta is equal to 40 degree. And net electric field will be equal to our Ex square plus Ey square root. So this will be coming as square root of 2 k lambda upon L. And in the vector form, we can write that our electric field will be equal to k lambda upon L, and this comes as minus x unit plus y unit. So this is our semi-infinite on a even point. Okay. A different way of asking the question, otherwise the derivation we have done it multiple times. Okay. So the way of question is little bit different. Next question. Consider a half infinite hollow cylinder shell that is one that extends to infinity in one direction. That is same as we did in case of semi-infinite wire with radius r and uniform surface charge density, that is our sigma. What is the electric field at the midpoint of the end face? And part B, use your result to determine the field at the midpoint of a half infinite solid cylinder with radius r, uniform density rho, which can be considered to be built from many cylinders shells. Okay, so these two are interrelated, and we are interested in finding out the electric field in case of our half, that is part A. Okay. So in part A, we have half infinite hollow cylindrical shell. Half infinite, sometimes it is also called a semi-infinite hollow cylindrical shell. And so obviously it's, you can say, we are given that we have a radius of the shell is given as r, radius of the shell is given as r, surface charge density is also given to us, surface charge density is given to us as sigma. Okay, and the point where field is to be found out is given as center of the end face. Okay, end face means, because it is semi-infinite, so other end will be infinity, so only one end will be at the origin, that is our end face. So we can say our field point, this field point will be center of the end face, center of the end face, and that is nothing but our origin. And because, okay, so we can just draw this cylinder. Suppose this is our cylinder and this is semi-infinite, okay, and this is the center of the end face that will be lying at the origin. And so because this cylinder is symmetrical with respect to the axis, so we can say that our by cylindrical symmetry, we can write our that radial component is going to cancel out. You can see that our radial component cancels and only axial component will be left. Only axial, that is our Z component, survives, or we can say is left. Let's call this as survive, not left. And finally, you can say that the direction of electric field. So we can say the field must point along a unit vector, Z unit vector, okay, because it is a positively charged cylinder. Okay. So you can say away from positively charged cylinder. Okay. Now let us break up this shell into charged rings. And like in case of the semi-infinite wire, we considered a small portion, that is of dq of thickness dx. Similarly, we are going to consider these small rings, and then we are going to integrate for this entire shell. So we can say that break the shell into charged rings. And let us suppose this is our charged ring, and we have center, and this is its radius r, and its thickness is dz. Okay. Thickness of this is, we have taken as dz. So we say that a thin ring at position Z and thickness dz. Thickness dz. So from here we can easily find out the surface area of the ring, strip rather, this shell. So we can say surface area of the strip. Let us call this as dA, and then this dA will be equal to over 2 pi r times dz. From here we can find out the charge on the ring. Charge of the ring, that is our dq, charge density multiplied by the surface area, and this comes as our 2 pi r times dz. And electric field due to this small charge element at a distance x, at a distance z. So you can say that electric field on the axis of the ring at a distance z. So it means this is our ring, this is axis, and we have point somewhere here. that is our z distance, and its radius is given as r. So we get this distance will be equal to over r square plus z square. And so we can write this as our electric field is equal to 1 upon 4 pi epsilon naught. This is our dq z upon r square plus z square, and this is our 3 by 2. Now we substitute our dq, and so we get this our electric field is equal to 1 upon 4 pi epsilon naught, and we get this as 2 pi r z dz r square plus z square 3 by 2. Now we are going to integrate for its semi-infinite length. Therefore we can say that the electric field will be equal to, we can take this pi and 2 goes by this, and we can take all the things outside. So we get sigma r 2 epsilon naught integration 0 to infinity, and this is a z dz r square plus z square 3 by 2. Once again we can assume that this denominator r square plus z square is equal to u, so derivative will be automatically giving us this z dz, obviously multiplied by a constant, so that will be much more easier to solve. So you can say that this electric field will be coming equal to as sigma r 2 epsilon naught, and this comes as 2 upon r, and I think 1 second, I made some mistake somewhere. Okay, so this will be 1 by 4, my mistake. So we get this, we get our electric field will be equal to, and this goes by 2, so we get the sigma r and 2 epsilon naught, and in the direction of our z unit vector. So this electric field due to a hollow semi-infinite cylinder, and we are going to use this relationship or this formula to find out for a solid semi-infinite cylinder. That is our part B. Part B we are said to be half infinite or semi-infinite solid cylinder. And in this case we are going to once again divide this solid cylinder into a thin cylindrical shells, because this solid cylinder can be said as stack of thin cylindrical shells. So we are going to consider a one shell and then we are going to integrate it. Only difference is that in this case the surface charge density is given to be different. Okay, so you can say for a shell we can write surface charge density, that is sigma is equal to rho times dr. Okay. And the field contribution from one shell, field contribution from one shell, and we already know this formula. We calculate in part A, that is of dE is equal to sigma upon 2 epsilon naught, and here sigma is equal to rho times dr and divided by 2 epsilon naught. Okay. And direction will be same. Okay, so we are integrating it radially. Therefore we can say that net electric field, that is E, will be equal to from 0 to r, and this is rho dr upon 2 epsilon naught, and this will be giving us rho r upon 2 epsilon naught. And in terms of direction, it will be same, that is about 2 epsilon naught, and this is a minus z unit vector. Okay, and magnitude is our same, only difference is of our charge density. Okay. So this completes all the 4 questions for today. Thank you.